In this discussion, we want to look at another way to get the Lorentz transformation, and this is very much akin to what is in the spacetime physics text, except done slightly differently. Now, what we want to do is we want to look at this as a transformation that keeps the metric distance the same. Just as rotations keep the Euclidean metric the same, and so do spatial translations, we now have spatial rotations. We'll keep our new metric invariant, and also temporal translations and spatial translations as well. But because we have a four-dimensional space, we have more degrees of freedom to play with, and we want to look at a transformation that mixes up, if you will, time and one dimension of space. So we'll consider the x direction. So we want to look at the following transformation, that t goes to t prime, x goes to x prime, and so remember, we're talking about boosts here, so we're boosting in the x direction, but the perpendicular directions are unaffected. So y is equal to y prime and z is equal to z prime. We're not going to consider those here on out. We'll just consider the two-dimensional spacetime of t and x, or t prime and x prime. And we want to do this such that the metric remains the same. Thus, we want to find the functions, essentially, that t prime as a function of t of x, we don't expect it to be a function of y and z, of course, and the function x prime is a function of t and x. Now, right now, we can keep it very general and say, well, we have really no idea what these functions are. We'll go with that. But we can think that we could expand it as a power series in t and x. So we want to consider, say, t here with a series of coefficients, a0 for a to the 1, t to the 1, b1, x to the 1, and so on, and the function in terms of x prime as well. And we can say we could do this because it seems natural to do that. And there's a little bit more general term you could have with cross terms of x and t, for example, in here. It should become clear and it should be obvious that those terms would not arise. So if we had a term of x times t, that would mean that the distance in the one frame or the other would change as a function of time, which is not what we really want. We want in each frame the positions to be static and stay the same, but they're moving with respect to each other. Now, we'll simplify this because, well, this is what's called standard configuration, but we take the case where the transformation is very simple, and it's called standard configuration, that when the times are equal, 0, we can always set that as we want, t prime is equal to t is equal to 0, that the origins match up. And that gives us immediately that the first two terms are obviously then 0. That's going to be our first simplification here. And again, in this case, we can think of this, say that's frame S, and then we have frame S prime at this time that the origins coincide. And we could call this x and this x prime. And say S prime is moving at some speed, at some speed v. All right. So what we're going to do is we're going to make an argument that the Lorentz transformation needs to be linear. But let's go into a little bit of why we expect that to be true. Okay, so we're going to check this, we'll say, well, let's say it's a nonlinear transformation, which we have here. So t prime is equal to a2t squared plus b2x squared. And perhaps higher terms, but we just look at this just to keep it simple. This will be enough, hopefully, to make our argument. And as we're essentially transforming from one inertial reference frame to another inertial reference frame that's moving at a constant velocity with respect to the first, and there's no gravity, will come later, that we expect that space is homogeneous and isotropic. It's the same. Homogeneous means it's the same everywhere, so that if you will, the positions should be the same no matter where you are in the space, the distance between them, say, and there's no preferred directions outside of the relationship between the two frames. But in each frame, it's isotropic. And remember, each frame is an inertial frame, so it's just like empty space. So if we do this, and we say have a series of events that are in frame S, and let's just say they're evenly spaced along the x-axis, when we do this transformation above, this is just a very hand-wavy explanation, since it's squared, it's going to look like this. It's going to be spaced, and they'll get wider further apart as you go. And again, we'll take this to be the origin. Now, the problem here is that now in frame S prime, space is no longer homogeneous. It's not isotropic either, but let's just go with homogeneity. Because, again, it should be clear that in this region, the positions are, roughly so far apart. But as you go further away, the actual, if you will, points in the manifold, if you will, get further apart. So the space-time in one region, which has these events very closely spaced together, are not the same distance apart at different places in the manifold. That's not allowed because they're both inertial reference frames, they're both homogeneous, and this having a nonlinear term violates that. Hopefully that should be clear. And again, space is no longer homogeneous nor isotropic. There is a preferred direction in that space along the x direction now. But to avoid this, we're going to say that the Lorentz transformation needs to be linear. And in that case, these events will be equally spaced in both frame S and S prime, though they may not be the same, of course. That's what we want. So our Lorentz transformations are linear, and that simplifies our transformation a lot to this form here, and we'll simplify the coefficients to A, B, E, and F. Here we write it in matrix form. It's another way to write that. It's much more compact and convenient, but it's just if you will, just another way to write this expression over here. Okay, now the feature that we want, that we're going to rely on here, is the invariance of the metric and the metric distance. Now, that's a typo. It's just distance. Okay, and the formal mathematical name for that is called isometry, the transformation that leaves the metric distance the same. And these are our physical transformations, continuous transformations. And we're going to ignore y and z because that's not really part of the story. But we'll just plug in now what we have for our and we're going to set ct equal to t for simplicity for the moment. We'll put it back in afterwards, but this just makes things look a little bit cleaner. But here we are. So what we did is we just plugged in for x prime and t prime. Now again, this was not written right. This is supposed to be t prime squared and x prime squared. So these are kind of the other way around. But again, you understand that we're just inserting the expression for the transformation. And we demand that these two be the same. But notice, let's square it out, and we get this. Now, when we combine terms, notice what we get. We want this to be invariant. So we have, first of all, notice, a squared minus e squared dt squared. Since that needs to be invariant, that needs to be 1, because that's the coefficient in the other side of the equation. So we have 1 is equal to a squared minus e squared. Let's do the dx squared terms next. So we get b squared minus f squared. That has to equal 1, because that's equal, minus 1 actually, but let's actually just go with that. And lastly, that should actually be minus, we flipped it. We flipped the terms here, so the sign's okay because we flipped these. And lastly, the cross terms, which is dx dt, we'll just forget about the 2 there, but we have ab minus ef. That has to equal to 0 because there are no cross terms in our metric. And so we get ab minus ef is equal to 0. We can play with this. It just says that ab is equal to ef. Or what we'll need in a moment, we could just write as e is equal to ab over f, and b is equal to ef over a. So we'll write that out. So what we can do is take these forms here and insert them into the above, taking those two. So we'll do it for both terms. But let's look at the first one. So we'll substitute e is equal to ab over f into here. And we get, by doing that, so we just take this one and square it. So we get a squared b squared over f squared. Factor out the a squared. So we get 1 is equal to a squared 1 minus b squared over f squared. And you can verify quickly that we can do the same for the other expression. We just get 1 is equal to f squared is equal to 1 minus e squared over a squared. But notice now that going back to here, we can rewrite this. If we divide through by f and we divide through by a, we get that b over f is equal to e over a. That's just rearranging from this expression. Well, notice this is b over f squared, and that's e over a squared. So these two are identical. And if those are identical and they both equal to 1, that means a has to equal to f. So all this this is just telling us that a is equal to f, but it also tells us immediately that b is equal to e. And that should be clear either by this expression or many different ways. And so now we can go back and we can solve for a, for example, here in this expression, and we get the following form. This. So now we eliminate f and e. So we just have a is equal to 1 over the square root of 1 minus b squared over a squared. Seems suggestive, but we're not there yet. But more importantly, our Lorentz transformation in general has simplified to this form. We have a, b, b, a. So we have two constants left, and we are getting closer to what we need. Okay, here's what we have. Now, at this point, we need to kind of look at a physical situation. So we want to consider a very simple case. We'll have a particle at rest in frame S. That means that dx, delta x over delta t is equal to 0, and it's going to be observed moving in frame S prime with some speed v is equal to delta x prime over delta t prime. So what we want to do is calculate that out. We're going to return the factors of c here, and this is just going to help us out. We'll write this as delta x prime over c times delta t prime, which is equal to v over c. Notice that's just dividing through by c there. And on the other side, we're going to have this expression here. Because now CT is just, and again, it's linear. So even though this is, because it's linear, we can just take this equation, subtract at one time, subtract it by the earlier time, and we get delta. So because it's linear, we can write this, just put the deltas in, it's fine. So this is using our transformation up above, where we have this one on top, delta t prime at the bottom. Simplify by dividing top and bottom by 1 over delta t. We get b plus a delta x over delta t, but delta x over delta t is 0, as we said. So these last two terms die, and we just get b over a. And so we find what we want. B over a is equal to v over c in this case. And thus, we immediately find, and again, this must be this will hold generally, because even though we looked at one specific situation here, what we defined up above for a and the transformation is general. So we immediately find that, well, a is equal to gamma, as we expect. Now, we also have the other forms here, which is, so what is b? We can quickly do some algebra here, that because we have 1 is equal to a squared minus b squared, going back to our original form, well, that's equal to gamma squared, because now we have a minus b squared. Solve for b squared, it's gamma squared minus 1, and let's write that out. So again, what we did here is we did some quick work here. 1 is equal to gamma squared over gamma squared. So this is 1 minus v squared over c squared. But that. All that tells us the 1's cancel, the minus signs become positive, take the square root, that b is equal to v over c gamma. And we're done. So our Lorentz transformation takes the following form, just written in the matrix version. You can do the quick multiplication out, that ct prime is equal to gamma ct plus beta gamma x, and so on for x prime. But this is our result, and that's what we want in the end. Now, this is a simple, in standard configuration for a transformation, or a boost, if you will, on the x direction. Now, with rotations and temporal and spatial translations, we have all of the transformations we can, and any legal or any physical transformation can be broken into a combination of our translations, spatial rotations, and our three Lorentz transformations. So x and t, another one that involves y and t, another one involves z and t. And that's it.